Hello, so I'm Jessica Ferweni, and I'm in Group 4 Control Systems, Classical Control Systems. And our task today is to solve the question you see on your screen. So, this question is basically on transfer functions, and I come to show how to solve this question. To begin with, you have to understand the circuits displayed below. So, one might ask, which kind of circuit has been displayed? And this circuit is a frequency-dependent voltage divider made up of capacitors and resistors as seen. So with this kind of circuits, capacitors, they behave differently when these in this kind of circuits, meaning they have different kind of frequencies which can be low or high. So at low frequency, the capacitor might behave as an open circuit. At high frequency, the capacitor might behave as a short circuit. So this kind of circuit helps to filter out everything and make a balance. And also to continue, the question asks us to find the transfer function. And a transfer function is basically the ratio between the Laplace of the output voltage over the Laplace of the input voltage. So at this point, one might ask, why do you need this? This Laplace transfer function helps you to know how much of the input appears in the output, and it also helps to know how to modify the signals at different frequencies. Go about it like that. So my colleagues would explain into details how this whole circuit was solved or simplified.
Hi, my name is Zipporah Apiakubi, and today I am presenting on circuit analysis and Laplace transform derivation using the circuit diagram given. So to solve this, we can use Kirchhoff's voltage loops, this being our first loop and this being our second loop. Applying KVL, V1 here equals the voltage drop across this capacitor, this resistor, and this second capacitor. We represent that mathematically by writing V1 of t equals this. And we represent it in this mathematical form, V equals IT of R plus that of the capacitors and the voltage. Taking Laplace transform to make our solutions easier, V1 of S equals I of S on SC1 plus I of S of R plus I of S on SC2. We simplify that to get our first equation. So that's our solution for our first loop.
My name is Obi Emanuela Japoma, third year computer engineering student, and you guys should calm down. It's not difficult at all. It may seem a lot, but it's not difficult. So we go on. The first equation is going to be V1 of S is equal to I of S, and then you bring the square bracket 1 over SC1 plus R plus 1 over SC1, which is going to be the first equation. And then we go to loop 2, and then we are going to apply KVL again. For those of you who don't remember, KVL is Kirchhoff's voltage law. So we come to V2 of t is equal to VR of t plus VC2 of t. We come down to find the integration of V2 of t, and then we are going to get I of t R2 plus 1 over C2, the integral sign I of t dt. Then we come down again, taking the Laplace transform. We are going to take V2s is equal to I of SR plus I of S all over SC2. Then we come down again to V2 of S is equal to I of S brackets R plus 1 over SC2 close bracket. So all we did in the second line, the V2S is equal to I of SR plus the IS all over SC2 is just a simplification of what we did up there. So we come down to the equation 2 which is I of S, is equal to V2 of S all over R plus 1 over SC2, which is our equation 2. So now we are going to substitute 2 into equation 2 into equation 1. I believe this one is basic maths. Once you get here, you should be able to, do it. So
Hello everyone, my name is Kofi Boache. So then, since we've already completed the first loop, we go ahead to find the voltage across the second loop through the output voltage as well. And so that one would also be equal to the voltage drop across the second capacitor plus the resistor, plus the voltage drop across the other resistor as well. And so that one would also, and so applying the KVL loop would also give us V2 of t is equal to the V of R plus the VC2. And so applying the Laplace transform like we did in the previous one would also give us I of SR plus I of S over SC2. And this time we are not making V2 of S the subject. We made I of S the subject in order to put it in the first equation to find the values. So the I of S would be equal to V2 of S over R plus 1 over SC2. And so substituting the second one, which is the I of S, into the first equation, V of S, we have V1 of S to be equal to V2 of S over R plus 1 SC2, open brackets, 1 over SC1 plus R plus 1 over SC2. And so finding the transfer function, which is V1 over V2, simplifies the equation to become C1 plus RC1 C2S all over C1 plus C2 plus R2 C1 C2S. And so we know that finally our transfer function across that circuit, which is the V2 over V1 of S, will be equal to C1 plus RC1 C2S over C1 plus C2 plus RC1 C2S. Thank you so much.
Hello. So with the same question, we are trying to use a different method to solve it. That's the block diagram. So this is the circuit again, and we want to find the transfer function of V2 of S over V1 of S. So with the block diagram, we will have to take the first loop, that's with the resistor and the capacitor. So that would be the L2 over here, and we take another loop across the whole circuit, that's from V1 to V2 over here. So taking the second loop, this one, we will have taking the second loop, it will be the summation of the voltage across the resistor and the voltage across the second capacitor. With the resistor, the voltage across the resistor, we have I of t R plus, then the capacitance voltage is also given like this. Now we take the Laplace, of both the voltages across both components, and this is what you're going to get. And with the representation of this in a block diagram, we have our IS to be the input source, and the V2 of S to be the output, and this right here will be the gain, the R plus 1 over SC2. That will be the gain.
Okay, so taking from loop B from this diagram is going to be V1 minus V2, which is equal to the voltage of VC1, that is for taking the loop B. So our equation is going to be V1 minus V2, which is equal to VC1 taking KVL is going to be V1 minus V2 is equal to 1 over C1, the integral of I of t dt. So from there, we'd have to take our Laplace transform, which is going to be V1 minus V2, which is equal to I of S over SC1. So I of S is equal to V1 minus V2 SC1. We got this by making I of S the subject. Okay, so right now our block representation is going to be V1 minus V2, with this is representing our input and I of S representing our output. Then SC representing our gain. So right now we combine the two blocks. The main reason why we combined the two blocks was because we can say that from loop 2, our IS was our input and from loop 3, our I is our output. So we can combine, making us get SC1 2. So the main reason for this summation is because of V1 minus V2. So from the feedback V2 taken from here to here, we present it by the summation. So V2, not forgetting our minus.
Hello guys, so continuing from where my colleagues ended, now that we have this block diagram of the circuits, we have to use the block diagram rules to reduce this circuit to a single block. Now block 1 and block 2 are in series. So since they're in series, we can simply multiply the two blocks. It's going to be SC1 in brackets R plus 1 SC2. And this is going to be the block diagram when we have reduced it. Now, to reduce now we have a negative feedback here. So to solve these circuits, we use the negative feedback law, which says that SC1 R plus 1 SC1 divided by 1 plus SC1 R plus 1 SC2. So this is the formula we are going to use to reduce this block. It's a negative feedback because we have the outputs that is connected to the inputs, and there's a unit gain here of 1. So there's a block here, but the gain is 1. So when we have this expression, we can now go ahead and simplify it using laws of algebra. So here we can take the LCM SC2 and take the LCM here SC2, and they're going to cancel out each other. When we simplify, we're going to have this expression up here. And we notice that S is common at both the numerator and denominator, so we can simply cancel out S. And when we do that, we're going to have this transfer function, which is RC1 C2S plus C1 plus C2 plus R2 SC C2S. So this is the transfer function of the block. So in summary, we can transform a circuit diagram into a block diagram and now reduce the block by using the block reduction rules, and we're still going to get the same answer. Thank you for watching.
Hello, hi guys. My name is Ajokum Hamid Jr., College of Engineering. How to convert from the block diagram into the signal flow graph. Sure, let's get into it. In order to convert from the block diagram to the signal flow graph, you need these two principles. That's the first one. All sampling points, all pickup points should be represented by nodes. Going back to the diagram, as you can see, the sampling points here and this point 2, point A and B, are both represented by nodes. Sorry, that's here. And all functional blocks should be directed by arrows. So this functional block, this whole block, are directed by arrows. G1 and G2, that's the SC1, and the block that contains R plus 1 over SC2 are both denoted or represented by arrows G1, G2. Thank you.
Hello guys, I'm Michael. So I'll be continuing from where my colleague ended. So after converting the block diagram into a signal flow, we have these properties. We have the forward path, and that's from the input A to the output B, and the forward gain, that is the G1 multiplied by G2, and there's only one loop here, and the loop gain is equal to negative G times G1 because of the feedback signal coming from B to A, and there's no touching loops, so it's 0 here. So we'll be finding the determinant. The determinant is equal to 1 minus sum of all loop gain plus sum of two non-touching loops. So the sum of all loop gain is the negative G1 times G2, and because we don't have any non-touching loops, it's equal to 0. So the determinant, we had 1 plus G1 times G2, and the associated path factor is equal to 1 minus sum of all isolated loops plus sum of product of two non-touching isolated loops. And here we don't have any isolated loops, and also no non-touching isolated loops, so therefore equal to 0. Then the associated path factor is equal to 1. So I'll end it here for my other colleague to continue.
Hello, I'm Papa Kojo Paying, and I'm here to use the Mason's game rule. So with the Mason's game rule, the rule states that the summation k equal to 1 to n with the numerator k times delta k from delta, where n stands for the number of forward paths, ek stands for the forward path gain of the forward path, delta k stands for the associated path forward factor, and then the delta stands for the determinant. So here we are applying the formula. So P1, D1, G2, and the delta 1 has a value of 1. So just the P1 will show. So that's what will be given over here. So this is the G1, G2. And then the value of the determinant is over here. This is the value of the determinant. So it is shown over here. So we have G1, G2 over 1 plus G1, G2. So we go back to the main circuits here. So here, G1 is represented by SC1 and G2 is represented by R plus 1 over SC2. So we come and do our substitution. Place it in this formula. Place it in this formula. So SC1 will go where G1 is, and G2 and R plus 1 over SC2 will go where G2 is. So then we have this, we do our simplification, and then we end up with this answer. So here's the transfer function is equal to RC1 C2x plus C1 over C1 plus C2 plus R2 C1 C2. Thank you.